In this lesson, you're going to use factoring to solve polynomial equations. So the steps really don't differ from quadratic equations, but let's remind you that first you should write your polynomial in standard form. In other words, set it equal to 0. Factor it as much as possible, and then you apply the zero product property. As always, it's typically easiest to understand with an example. So this is already in standard form equal to 0, so I'm going to begin by factoring out my GCF, which is y squared. I will divide each by y squared, which produces y minus 5. This is factored. So I'm going to take each factor and set it equal to 0. So I'm going to have y squared equals 0, or y minus 5 equals 0. How do I solve the first? I would take the square root of both sides, which would produce y equals 0, or here I would add 5, and I get y equals 5. Now, the one thing I want to point out is that in this particular answer, 0 is there twice. It has what we call multiplicity 2. So I'm just going to write that underneath of here, multiplicity 2. So your three solutions are y equals 0, y equals 0, or y equals 5. If you just list it once, that's okay, but it will be helpful as we move forward if you list it as having multiplicity 2. In number 18, this one is not in standard form, so I'm going to begin by subtracting 50c from each side. This produces 18c to the third minus 50c equals 0. So now I'm going to factor, and I believe 2 is the greatest common factor and c, so I'm going to divide both by 2c, which produces 9c squared minus 25. Now I'm going to look at this quadratic binomial in here, and that looks like my favorite pattern, the dots pattern, or difference of two squares, which factors into 3c plus 5 times 3c minus 5, and I'm going to bring down my GCF. Each factor is linear, so I know I cannot factor it any further. Now I apply the ZPP, which says 2c equals 0, or 3c plus 5 equals 0, or 3c minus 5 equals 0, and I will solve each of these. Dividing by 2 in the first produces c equals 0. It's only there one time. In the next, I'm going to subtract 5, which gives me 3c equals negative 5. Divide by 3, and I get c equals negative 5/3. Similarly, in the next one, I add 5, divide by 3, and c equals positive 5/3. So my three solutions are here. Hopefully you start noticing things like, well, when it's to the third power cubic, we get 3 solutions. In number 19, I'm going to bring everything to one side, and I'm actually, even though it might seem like less work to bring the g to the third over to the right, I'm actually going to bring each of these over to the left because I always like my leading coefficient to be positive. It's easier to factor. So this will be g to the third plus 3g squared, because when I add it, it will switch signs, minus g minus 3 equals 0. So I have a polynomial with 4 terms. So I'm going to try grouping. I'm going to group the first two. I'm going to make this plus a negative and group the second two. So my GCF of the first binomial would be g squared times g plus 3. I'm going to factor out a negative 1 to make this be g plus 3. Now I look for a common binomial factor. I notice they both have a g plus 3. So I'm going to bring that out to the front, and you're dividing each by g plus 3, which produces remaining g squared minus 1, and again, this is all equal to 0. This quadratic binomial factors a little further. It's my favorite pattern, the difference of two squares. So it factors into g plus 1 times g minus 1, and I'm going to bring down my initial GCF. I now apply the zero product property. So g plus 3 equals 0 gives me g equals -3. Then I get positive 3 because I add 3 to both sides. Let me fix that. It should be g equals 3 or g equals 1. So 3 solutions. If I were you, I'd try 20 on your own. Hit play when you're ready to check your answer. Should have started by placing it in standard form, which is 2f to the 4th minus 13f squared minus 45 equals 0. So first thing I look for is the greatest common factor. I don't see anything that pulls out of all three terms. So next, since it's a trinomial, I'll try tic-tac-toe off on the side, where I would have 2f to the 4th here, negative 45 in the middle, and my checking term is negative 13f squared. Now your factors of 2f to the 4th, well, coefficient would be 2 and 1, and then it would have to be f squared and f squared. Don't ever do like f to the 3rd and f to the 1st, where that would equal f to the 4th. It's never going to add to f squared in the middle, okay? So you need them to match here. Factors of negative 45 would be 9 and 5. I'm going to try negative 9 and positive 5, as that would multiply these two to give me negative 45. Now I multiply horizontally, would be negative 18 f squared and 5f squared, and I got it. That sums to negative 13 f squared. Okay, so my factors are on the diagonal. One of them is f squared minus 9. My other is 2f squared plus 5 equals 0. I'm going to see if I can factor any of these further. And this first one, again, is my favorite pattern. It's a dots pattern. It's going to factor into f plus 3 times f minus 3. The second one is quadratic. I don't believe that factors any further. There's no GCF, and it's not the dots pattern, so I'm out of factoring tools. But I still go and I apply the GCF, which gives me f plus 3 equals 0, or f minus 3 equals 0, or 2f squared plus 5 equals 0. So the first two are simple. I subtract 3, and I get f equals -3, or add 3, and I get f equals positive 3. This last one, I am going to use the square root method. It's quadratic, but I'm still going to subtract 5, which would give me 2f squared equals -5. And then I'm going to divide both sides by 2, which gives me f squared equals -5 halves. Then I take the square root of both sides. The moment I do that, I know I need a plus or a minus out front from my big unit on quadratics, which gives me f equals plus or minus. I'm going to pull an I out front, the square root of 5 over the square root of 2. I'm just splitting that up into 2. And lastly, I remember that I cannot have a square root in the denominator, so I'm going to rationalize that by multiplying by root 2 over root 2 to get two complex solutions of plus or minus I root 10 over 2. So those are two complex answers, and here are two real ones. So interestingly, if you look at this, this was a quartic function. It was to the 4th power, and we have 1, 2, 3, 4 solutions. That's not a coincidence.